Okay, now we move towards a very interesting topic of what do you call the covariances. Covariances are the topic of very much interest actually. They are of a very practical importance. So we'll focus today on defining covariance and then coming up with the basic properties of the covariances, and in fact the sum of variances actually. Sum of variances, because the sum of variances can be of the random variables can be written in the terms of the covariances. So what in a simplistic manner, if we can get into the kind of a more detail of it, what the covariances in general basically tell you that if you have, for example, two random quantities, like the two random processes, so imagine that you have shares of the two companies. There are, say, two commodities, okay? So there are shares of two companies, and you want to know that are the prices of the share of these two companies have something to do with each other or not? Are the two processes kind of depends on each other or not? In other words, that if the price of, say, one commodity is increasing, the price of other commodity is increasing as well, or if the price of one share is increasing, is it the case that the price of other share is increasing? In that case, we will say that they are positively related actually. For example, if the price of petrol will increase, the price of all those things which depends on petrol will also increase. For example, traveling, for example, different kind of things, the product that are based on the petrol. So I would say that petrol, the prices of petrol and the products and the things then depends on the petrol, they have a positive correlation. If one increases, the other increases as well actually. So there is a kind of a strong dependence between them. But you can also have a case actually that when the two things are not related actually. Okay, the two things are completely unrelated. There are two processes which has nothing to do with each other actually. Okay, so for example, you can have the price of the petrol. Okay, it has nothing to do with, for example, the price of some kind of a product which does not depend on the petrol actually. So it has nothing to do directly with the prices of the vegetable actually. In some sense they do have, because okay, there is a cost to carry the vegetables from one place to another place, but you can think of two kind of products whose prices have nothing to do with each other. Price of a gold has nothing to do with, say, for example, price of the tomatoes actually. Okay, so the things are unrelated apparently. So you're going to say there is no covariance between these two quantities, and we will later on talk about the correlations as well, which is like making it more concrete. And you can have a kind of a negative correlation between our covariance between two quantities actually, that okay, if the one quantity is going up, like the other quantity is, what do you call, going down actually. For example, you can take a physical example. If you say that if you have a random physical quantity, their pressure and volume are inversely proportional to each other. So if you increase pressure, the volume decreases. You decrease pressure, the volume increases actually. Okay, or you can have many different kind of things that basically which when one price goes up, the other goes down naturally. Okay, so in that case you have what you call you have a kind of a negative relationship between these, and negative covariances between them actually. So the covariances is essentially that if you have two random quantities, what is the dependence of do these two quantities, these two random quantities, processes depend on each other or not actually. Okay, so the covariances are important in studying that. So before defining the covariances, let me prove a little interesting proposition. I'll prove this in continuous time, which says that imagine I have two random variables x and y that are independent of each other. Okay, so x and y are independent of each other, independent. Then for any nice function, say f and g, if you compute, say, expectation of f of x times g of y, and x and y are independent of each other, then this is same as computing the expectation of gx times expectation of g of f of x times expectation of g of y actually. In other words, if the x and y are independent of each other, then any two functions of x and y are also independent of each other. They do not depend on each other actually. So how can I quickly, for example, show it? So I can treat this expectation of f of x times, say, g of x, g of y as a single function. Okay, let's call it a function z that depends on x and y, and z of xy is f of x times g of xy. Then we know that how to compute the expectation of z of xy. So this is going to be that, okay, you compute the double integral of f of x multiplied by, okay, g of x times the joint PDF of x and what do we call y dx actually, dx dy, okay, dx dy. This is what that you're gonna get from minus infinity to infinity, minus infinity to infinity. Okay. I know that f is not a good choice. I mean, maybe we can change the f by h because we are. So this would be, otherwise repeated actually. Okay. So h and g. So let's call h. Let's call it g of y. Okay. Now, since x and y are independent of each other, minus infinity to infinity, minus infinity to infinity, h of x times g of x, then this PDF is basically the product of the marginals of x and y, or the PDFs of x and y. Fy of y, dx and dy. In fact, what you can do, you can pull out, for example, the first integral is with respect to x. So this, the functions of y, okay, the functions of y are like the constants actually. So if you wish, you can pull this out of the integral actually. So what you can do is that even you can write it as a g of y, okay, g of y, fy of y, okay, an integral from minus infinity to infinity, h of x, gx of h of x, fx of x and dx, and times what do you call y actually. Now what would be this quantity? This quantity is really the expectation of h of x actually. This quantity is expectation of h of x. And expectation of h of x is going to be, so in other words, this entire integral can be written as expectation of h of x. And expectation is a number. So if you wish, you can pull this out of integral actually. So you're going to have expectation of h of x times minus infinity to infinity, g of y times fy of y dy. Okay. Now, what is this quantity? I mean, if you wish, you can call this as expectation of g of the random variable y actually. So, what does this show? If x and y are independent of each other, then any functions of x and y are also independent of each other. Okay. Now, let me define what you call the covariances actually. So the covariance, so So the variance is like the deviation from the mean actually in one dimension. So the covariance is a two-dimensional analog of the variance actually. Okay, so when you have two random variables, you will not talk about the variance of x and y together. No, you'll talk about the covariances. So the covariance is, really like, deviating from, on average, that how much x and y both deviate from their mean actually. Okay, so it's a two-dimensional version of variance. Okay, so the definition of the covariance of x and y, okay, is that it is the expectation of expectation of x. In other words, that it's an average of the product, that how much x deviates from its mean times how much y deviates from its mean actually. Okay, how much y deviates from its mean. So it's the product of, so on average how much this so the covariance is the expectation that average that how much x deviates from its mean times y deviates from its mean actually. So this kind of gives you what you call the covariances actually. Okay, and covariance are important to define, as I said, what you call the correlation, which tells you that how two things are related with each other, positively, negatively, some other way. A simple remark is this, that the covariance of xy can also be written as expectation of xy minus expectation of x times the expectation of y actually. So this is also a fact that follows from definition. How? I mean, if you write this product explicitly, okay, if you take the covariance, the definition of covariance of xy, and you take, say, expectation of xy minus x expectation of y minus y expectation of x plus expectation of x times expectation of y, then by the previous property that the expectation of sum is the sum of expectation, then this is same as expectation of xy minus, so you're going to have expectation of x times this number actually. Okay, so if you wish, you can pull this out of the expectation. In other words, that this is going to be expectation of y minus expectation of, say, y times expectation of x, and plus expectation of, is it going to be plus or minus actually? It is going to be plus. Yes, plus expectation of x times expectation of y actually. Okay. Now, if you see that if this expectation of any random variable is like a number, so this is a number multiplied by x. So if you wish, you can pull this number out of x. So you're going to get expectation of x times expectation of y. You will also get from here expectation of x times expectation of y, which will be cancelled out with this, and you get what you call this identity. So you can treat also this as the definition, that covariance of x and y basically tells you that how much the product of the deviation, product of the expectation is differing from the product of expectation of the product is differing from product of expectations actually. Okay, so these are some of the basic properties. Now let me write a proposition which is going to list some more properties of the covariances, some more interesting properties of the covariances. This is proposition, say 4-point proposition. which says that following is true for the covariances. Covariance of xy is same as the covariance of yx, which is true by definition. Doesn't matter, in x, in the place of x, if you substitute y, and in the place of y, if you substitute x, you still get the same expression. Okay. The second thing is that if you take, say, the covariance of x and x, covariance of x with itself, you should get the variance of x, and which is true actually. In the place of y, if you substitute x again, so this will become expectation of x square minus expectation of x times expectation of x whole square, which is the definition of the variance of x actually. So this is the second important thing. So if you have the covariance of, say, a constant a multiplied with xy, this is same as a times of the covariance of, what do you call, xy. Okay. And the covariance of, say, sum of, say, I equal to 1 to n, xi, and the covariance of random variables, say, j equal to 1 to m, xj, okay, is equal to a double sum I that goes from 1 to n and a double sum j that goes from 1 to m, the covariance of xi yj. Okay, so covariance of the sum is the sum of the covariance actually. So it's kind of linearity property of the covariances. So these are the basic properties of it. Proof of first and second is trivial. Third is also trivial. Think about it. If you have the covariance of ax and y, this would be same as expectation of axy times expectation of ax times y. So you can pull a out of expectation here and a out of expectation here, and then pull a out of both expressions. So you will remain with a times covariant of xy. So these three are really trivial actually. So you should do it for, what do you call, yourself. The next is the more interesting part is to prove, what do you call, 4 actually. Prove 4. Okay. So let's give this sum x equal to I equal to 1 to n xi a name x, and y j equal to 1 to m a name, what do you call, yi. Okay, and let's assume that expectation of xi is a number nu I, and expectation of, say, yi is a number nu I actually. Okay, then what would be the expectation of x? The expectation of x is going to be the sum of expectation, in other words, sum that goes from 1 to n mu I, and the expectation of y is going to be a number that is going to be a sum that goes from j equal to 1 to m and nu j. Okay, this is what is going to be the expectation and expectation of y. Now, covariance of, say, the sum that goes from I equal to 1 to n xi and I j equal to 1 to m yj is like computing the covariance of x and y. And by the identity, this is same as the expectation of xy minus expectation of x times the expectation of, what do you call, y. This is what that you're gonna get. Now, what would be the expectation of xy? The expectation of xy is going to be a product actually. So it's a product of sum that goes from 1 to n, xi multiplied by the product that goes from j equal to 1 to m and xj. Yj. Let's try to yj. times minus expectation of x is this sum I that goes from 1 to n mu I times sum j equal to 1 to m and nu j. This is what it is going to be. Now, it's not difficult to see that why you're going to have a double sum. If you treat, say, this first quantity, so this sum is like a sum actually, okay? So this sum is like a number, okay? Now if I give this a quantity a name, for example C, okay, or maybe say x, actually we know that this is already x. So this x is being multiplied by this sum actually. So this x would be multiplied with each of the term in yj. Hence I can say, I can take this entire bracket and multiply it with each term of the yj. So you're going to get what? It's going to be a sum that, or I can take, for example, this term and multiply with each term of the xi. So this is going to give me I equal to 1 to n, okay, I equal to 1 to n, and multiplied by, okay, j that goes from 1 to n, say yj times, what do you call, xi, okay, minus, you can do the same actually here, the sum that goes from 1 to n mu I multiplied by the sum that goes from j equal to 1 to n and mu j, okay. Now this xi can be multiplied with each mu j. So it's going to be, I can write this as I equal to 1 to n times j equal to 1 to m. So each xi is multiplied with yj, so it's going to be xi yj minus each mu I multiplied with mu j. So it's going to be a double sum that goes from y equal to 1 to n and j equal to 1 to m and mu I mu j, okay. So if I wish, I can put these sum together and I'm going to get I equal to 1 to n and j equal to 1 to m and xi okay, so I missed something very important. So there is an expectation here always, okay, so there is always an expectation, okay, in each term. So now if I have an expectation of xi yj's, so I can put an expectation here, okay. This must be same as the expectation of sum is the sum of expectation. This must be same as expectation of xi yj minus mu I and mu j. Okay, this is what that you're gonna get. Now if you see, mu I is the expectation of xi and mu j is the expectation of yj. So if you see, this is what is the precise definition, I equal to 1 to n and j equal to 1 to m. This is the precise definition of the covariance of xi yj, because what would be the covariance of xi yj? So it's going to be expectation of xi times yj minus expectation of xi times the expectation of yj. So we have this precise expression actually, okay. It seems a complicated expression, but it's not really a complicated expression actually. What are the benefits of these properties? So for example, what are the benefit of all this actually, especially this last identity? One of the benefit of this last identity is that previously, I mean, if you remember, we said that the sum of the expectation is the expectation of the sum actually. Sum of the expectation is equal to the expectation of the sum. The question is, how about the variances? Is the variance the sum of the variance of the sum is equal to the sum of the variances? The answer is no actually. If you compute, for example, variance of sum I equal to 1 to n xi, then we just saw the identity that the variance of x is basically the covariance of x actually. Okay, covariance of x. So the variance can be written as the covariance of sum that goes from I equal to 1 to n xi, comma sum that goes from I equal to 1 to n xi. So this is what is going to be the covariance. Now this covariance by this identity can be written as a double sum that goes from I equal to 1 to n and j equal to 1 to m. The covariance of xi yj, so this is what that you're going to get. Now I and j, n and m can be two numbers. For example, I can have a sum, so imagine I have a sum that goes from I equal to 1 to 3, and I have a j that goes from I equal to 1 to 5, and I have, this sum xi yj. So if I write it explicitly, I can say that this is going to be equal to what? So I can write it as, so there can be the instances when they two are equal, there can be the instances where these two are not equal. In other words, I can write this as a sum that goes from 1 to 3 and that goes from say 1 to 3 xi yi, okay, or maybe what we can do, we can write this as the sum in the kind of a two sums actually, okay, in the kind of two sums where I and j agree and where I and j don't agree. For example, I is less than j. So when I and j would agree, this will become xi yi, so this will become xi yi, and when I and j don't agree, so this will be like xi yj, okay, xi yj. That's how it is going to be. Now you have the same case here actually. Now I can break this sum into the two parts, one where the xi agree, so it's gonna be a sum that, for example, that goes from I equal to 1 to n, and you have the covariance of xi and xi where I and j agree with xi and yi, okay, xi and yi. So all these are xi's actually, yes. Xi and xi plus the sum when I is different from j. Maybe I is less. If I is different from j, then you have trichotomy law, three possibilities. Either I is less than j or j is less than I. So let's try to say I is less than j. So this would be equal to what? The covariance. So it's also a double sum. Xi xj. Okay? Xi xj. Now what is this guy? Covariance of xi. This is really the variance. I equal to 1 to n. Variance of xi. You may also say that you have here I does not equal to j. Okay, I does not equal to j. So this would be equal to, you can write, now if I is not equal to j, there will be terms when I is less than j, and there will be terms then that where I is bigger than j actually. But the both will be equal in the quantities. Okay, I would say that try to make sense of it more explicitly. Okay, and it's good that you should deal with these abstract sums. So when I is less than j, so you have the two possibilities. The double sum when I is less than j, covariance of xi xj, and the sum when j is less than I, covariance of xi, xj. But these two sums would be exactly equal to each other. For example, if it is x1, x3, and here you have x3, x1, x1, x3 is same as x3, x1. Because of the symmetry, the covariance of xy is equal to yx actually. So if the covariance of x1, x3 is going to be same as covariance